Okay. You are using the computer audio. Hey, I think I've got a customer, Bryce. I've got Bryce on here.
Hello, how's it going?
Not too bad. It
Good.
quit raining. I just went outside.
Yeah,
Quit raining now.
all that,
Let's see.
saw that.
Trying to make this, trying to what they call pin myself. There we go. Yeah. That didn't do it. Hey, yeah, there we go. Tuesday, September 1st. Okay. And we've got Bryce and Nathan so far. Good going. Let's see who else we have here. Oh, we got a big crowd. Brian, Bryce, Dawson, Braxton. We got a good crowd. Julian, Taylor, Daniel, Mohammed, Nathan. Yeah, good crowd here. Okay, well, I've got 11 o'clock. I think we should get started. Let me remind myself what we're studying. 1st of September. Let's see what it says here. This says, First of September. Well, I think we're supposed to do compressibility next time. I think that really is next time. We might get into it today, but that's definitely on Wednesday. We're still, I'm still hoping for you to understand PV diagrams. Okay. All right. Well, let's just get started, shall we? Now, the emphasis today, I think, should be on the ideal gas law. Maybe we should talk about that for a minute. We've got a good class here. Now, my favorite version of the ideal gas law. Let me see if I can bail this stuff out of here. I don't want to do that. No, I just pinned. I just pinned somebody. I think I just goofed up. Now we're okay. My favorite version of the ideal gas law is it's like that. And let's just use it on argon. Now, argon is a ideal gas. It really works great. It's one of the noble gases. I'm sure you've heard of the noble gases. What is it? Argon, neon, krypton, xenon. Sounds like I'm missing one. There's neon, argon. I think there's 5 of them. Let's look up some stuff about argon. Yeah, get your book. And we need we need the ideal gas law constant for argon. Okay. Here we go. Trying to find it here. And argon. I'm still looking. Aha. Argon. That R right there is your gas constant, and it's 0.2081. Kilojoules per kilogram Kelvin. So we got that. Excellent. Okay, now what?
Where did you find that number?
Oh, thanks for asking. That's in Appendix A. It's table A.5.
Thank
Now,
you.
there's another way to get it. It's also equal to the universal gas constant divided by the molecular mass. Now, the universal gas constant, from memory, I think it's 8.314, but we better look that up. Hey, did I do that right? I don't know. That could be wrong. Let me shop around a little bit here. Gas constant. Maybe you could help me find it. Look in the index. Go ahead.
The math of it all worked out. I divided the.
Yeah.
your-
Well, I did that from memory. That could be wrong. I was going to show you where that is, but I couldn't find it. But the molecular mass for argon is 39.948. Now the units on this are kilojoules per kilomole Kelvin. And what these are is kilograms
Hello.
per kilomole.
Hello.
Now who just spoke up? Who was that?
Okay.
I'm sorry, who? So say one more time, please.
I think that might have been someone on accident.
Oh, okay. Well, let's see what this is. Here we go. 8.314, that's from my memory. I'm not sure about it. 39.948. I get 0.208. Well, boy, Jove. I get 0.2081. And look at the units. They'll be kilojoules. See, the kilomoles cancel, and you're left with kilogram Kelvin. You can get the gas constants if you know the molecular, what they used to call molecular weights. They're really molecular masses, okay? So I thought I'd show you that. Or you can just look them up in table 8.5. See, now, like for oxygen, for instance, if you wanted to do oxygen, is that how you spell oxygen? It looks pretty good. You know what it would be? It would be 8.314, because see, that's for all gases. That's the universal gas constant. And you probably know molecular oxygen is that's 32, isn't it? Isn't oxygen 32?
Yes,
Now,
sir.
if you weren't sure, I could look that up. Let me see. Oxygen. Well, actually, the book is 31.999, but that's dang close to 32. You know it. But you could get this if you don't have a table. If you're stranded on a desert island, your ship sank, all there is one palm tree and some coconuts. But see, you know it's about 32. Molecular oxygen is 32. You could get the gas constant by going 8.314 divided by 32, and you get 0.2598. Now let's see what it is if you looked it up. Oxygen. Well, boy, Jove, if you look up oxygen in the book, oh, Jesus, yeah, there we go. It's 0.2598. Of course, now you know the units. It's kilojoules per kilogram Kelvin. Ta-da. We're going to do argon, though, and so we don't need that oxygen anymore, but that was fun, wasn't it? Let me erase all that. Now, what if you were doing inglés, senor? Habla inglés?
See,
Well, then, well, we'll get to that. I was going to go ahead and do this argon problem, and then it'd be fun to do one in English. Yeah, you've got to be able to do stuff in English. But there's a problem in your book. It's problem 266. Let's do that together. Help me find it. 266. I'm trying to find it. 266. Yeah, okay, here we go. 266. Says here, argon is kept in a rigid 5 cubic meter tank at -30 and 3 megapascals. Determine the mass using the compressibility factor. Hey, I'm going to have to explain this compressibility in order to do this problem, huh? What is the error if the ideal gas model is used? Well, we'll show you. Okay. Well, let's do the ideal gas model. See, that's it. This is the ideal gas. Only you might prefer this equation here. P big V is equal to mRT. They're both correct. It's just that that's a little v and this is a big V. And you know the difference. One of them is specific volume and the other one is volume. This M refers to mass. Well, why don't we do both of them? That'd be fun. Let's do both. Okay, here goes. We're doing problem 266 in the book. And we're going to have to show you about compressibility here in a minute. All right, well, let's do this first one. PV. Okay, what's the P? Well, if you read the problem, they said it's, got lost there. They said it's 3 megapascals. You have to use kilopascals when you use this equation to get the units to work right. And we're going to solve for little v. We know R for argon. And now here's the catch. The temperature is -30 Celsius, but it's got to be in Kelvin. See, -30 Celsius is equal to 243.15 Kelvin. I'll be glad to explain that. If anybody needs me to, just speak up. I think I did that right. So we're going to put that right here. See, the kelvins will cancel out. I think the units are all fine, and we can get our specific volume. Go ahead and get it for me. Get your calculators and tell me the specific volume. Okay, I've got what I think is the specific volume. How about one of you? Tell me, what did you get?
I got 0.1687 cubic meters per kilogram.
You know what? I got the same numbers, but I got 0.0167 like you're talking about. Now, who am I talking to?
This is Bryce.
Bryce? Bryce, I'm getting, one of us is probably right. I'm getting 0.016. Actually, I got an 8.7 cubic meters per kilogram. Do yours again. I'm going to do mine again. Go
Yours
ahead.
is right. 0.0168.
There we go.
7.
Yeah. We're okay. So we're happy. Bryce and I are happy now. But now they wanted the mass. Okay, well, here's how you get the mass. See, the mass is equal to the volume divided by the specific volume. Okay. This problem here, if you read it, says you have a 5 cubic meter tank, and you'll divide that by the 0.01687 cubic meters per kilogram, and we'll get our mass. Here goes. Okay. Ta-da, I got it. I got a 296.4 kilogram. Gee, that's a lot of argon. Pretty heavy. But you know what? 5 cubic meters is a pretty big volume. 5 cubic meters. Let's see how much that is. Let's see. That would be 1.7 meters on a side. One 1.7 meters, 1.7 meters, 1.7 meters. And you know how long a meter is. It's longer than a yardstick. That's quite a lot. Yeah, I think that's right. Now let's use this formula. We use this formula. Now let's use this one. Okay. I need some room. How about right here? There's some room right here. Okay, the pressure is 3,000 kilopascals. The volume is 5 cubic meters. We're solving for the mass. R is 0.2081 kilojoules per kilogram Kelvin, and the temperature is in Kelvin, 243.15 Kelvin. Okay, solve that for M and tell me what you get. Go for it. Well, I'll tell you what I got. I got 296.4 kilograms. I got the same answer I did the last time. How about you?
Same.
Yay. So, yeah. Excellent. Anybody else? I'll give you another moment. I need a couple more people to say uh-huh.
Yeah, we got the same.
Uh-huh.
Yay, I heard an uh-huh. I sure did. Well, they wanted us to do this with compressibility. Now that's supposed to be, we're supposed to study that next time, but hey, let's just get a tiny bit ahead because we'll probably get behind sooner or later. There's another way of doing this. It's called compressibility. I just need some room here. Well, we'll just say goodbye to all this, I guess. Now to do compressibility, what you have to do is, we're going to use this equation here. I really prefer this first one. They're both fine, but what it amounts to is it's the same equation except you've got this what they call the compressibility factor, and it gives you a slightly more accurate answer usually. In this case here, since argon is so close to being ideal, that Z is going to be close to 1. But here we'll go ahead and show you how to get it. Now to get it, you first have to find what they call the reduced pressure. And what that is your pressure divided by your critical pressure. Now you know what critical pressure is. It's at the top of your vapor dome. We've studied those vapor domes. Now the pressure in this problem was, well, we'll put it in megapascals. It was 3,000 kilopascals, but that's 3 megapascals. And the critical pressure for argon is, at the top of the vapor dome for argon, it is, let me find it here. Argon, it is 4.87 megapascals. That's on table A.2. Look on table A.2 and you'll see it there for argon. And then we need the reduced temperature. The reduced temperature is the temperature divided by the critical temperature. Well, the temperature is 243.15 Kelvin. And the critical temperature, that's the temperature at the tippy top of the vapor dome. On table A.2 for argon, it is 150.8. Or 2 numbers, and then I'll show you how to get the compressibility factor to plug in here. It's going to be close to 1, because I know it will be for argon. Argon is one of the noble gases. Okay, plug that stuff in. Let's see what we get. 3 divided by 4.87. 0.62 maybe. 243.15 divided by 150.8. I'm getting 1.61. Almost done. Now what we're going to do is we're going to go to a graph. And this graph is figure D1. Figure D.1. And I'll show you what it looks like. It's in the back of your book. See where I'm wiggling my finger here? That's it. That's figure D.1. You got the reduced pressures on the bottom, and the reduced temperatures are these wavy lines up here. So what I'm going to do is, I'm going to take the reduced temperature, or pressure, I mean. Okay, I'm going to take the, I don't know if you guys can see this. Yeah, not too bad. Now what I need is reduce pressure of 0.62. Okay, now guys, look here. There's 0.01, there's 0.1, there's 1. You know what? 0.62 would be right in here someplace. I've scribbled on that. Let me erase that scribble. See, if that's 0.1, that's 0.2, that's 0.3, that's 0.4, 0.5. 0.6, here I'll make another scribble. 0.62 is right there where I made an ugly mark. And we're going to come up here till we hit the reduced temperature of 1.6. There is no 1.6, but there's a 1.5. And if you come up here to where it's 1. Go a little bit more, because 1.6 is a little bit bigger than 1.5. And where my pencil tip is, you come over here to the left, it looks like about 0.96 for your compressibility. I don't know if that made a lick of sense to anybody, but that's how you do it. And so the Z from that table is I told you it's close to 1. It's 0.96. So now we're going to get the specific volume, but this time we're going to plug in 0.96 instead of a 1. See, there's a 1 right here. See it? But we're going to plug in the 0.96. And what you'll get for the little v here, when you plug that in, it'll be different, won't it? I've lost what it was the last time. Here, you can put the Z in here for compressibility. You can put a Z in here. And if you do, you can get your mass. I think to find the mass, you'd have to divide by 0.96. So you guys can work it out, but here's what you'll get. I think it'll be a little smaller. It'll be 296.4 divided by 0.96. It's 308 rounded off to 0.8. So argon is not a perfect ideal gas. And in the ideal gas law, if you use compressibility, that Z is 0.96 at those temperatures and pressures. It might be different for something else.
Professor,
Yes.
this is Nathan. I have a question
Hi,
about.
Nathan.
Hey there. I got a question about figure D1. I'm a little bit confused about that graph.
Hey, I don't blame you, Nathan. I don't blame you one little bit. Back to that graph for Nathan. We need a reduced pressure of 0.62. Nathan, 0.62 is in between 0.1 and 1. Do you agree? 0.6 is bigger than 0.1, but 0.6 is smaller than 1. Right, Nathan?
Are we talking about the left side of the graph?
We're talking about this bottom line here is reduced pressure.
Okay, let me be specific with what I'm confused
Yeah,
by.
you go ahead. Go ahead.
I'm looking at the very bottom. It says reduced pressure,
Yes.
and I'm looking at 0.1 to
Yes.
1. But then I'm
Yes.
also looking at those vertical lines there that say like
Right.
0.7, 0.8, 0.85, 0.9.
Right.
I'm confused by, I guess, by those two sets of numbers.
Those are reduced temperature lines. Those vertical lines are reduced temperature lines.
Okay.
Now you find 0.62. It's about where I made my ugly mark right there. And you go up and you have to cross where it says 1.6. It's right up here. It's way up towards the top. It's about 0.95, something like that. 0.96 for the Z. We'll do some more. It'll dawn on you, okay?
So you're not looking at reduced temperature. You're just looking at reduced pressure, and then going up until you reach a Z factor.
Right. You look at reduced pressure, you go up and find where the reduced temperature line crosses it, and then you go over here to the left and get the compressibility factor Z.
Okay. Make a little bit more sense. Thank you.
Yeah, it'll make more sense if we do some more of them. So let's do some more. That was fun.
Hi, Professor.
Yeah, go ahead.
Okay, after the next exercise, can we please do 241?
Sure.
Yeah, I just get a little bit confused on
Sure.
that.
Tell me your name.
My name is Reagan. This is Reagan.
This is Reagan. Okay, Reagan. Well, let's do it right now.
Okay.
Let me find this 241, Reagan, and we'll do it right now, and then we'll get back to using this ideal gas law stuff.
Okay.
241. Is that what you said?
Yes.
Okay. Okay. Now this is R134A. Let me say goodbye to all this for right now. Now, R134A is, that's what you've got in your car, Reagan. Reagan, do you have air conditioning in your car?
Yes, I do.
Well, you've got R refrigerant 134A in your car. Now, let me tell you what that is. Just out of fun here, I'll show you what that is. And if I can find it. R134A. I'm going to find it here. Let me keep looking. Yeah, here it is. Now, we're gonna write down what Reagan's got in his car. And then we're gonna do this problem. I think it's problem
241.
Is it 241? Is that what it is, Reagan?
Yes, 241. Yes, that's
Yeah,
right.
we're going to do that here in just a minute, but it's dealing with the refrigerant R134A. And in the back of the book, it says, this is table A5, that the structural formula, oh no, this is the chemical formula. The chemical formula for refrigerant R134A on table A.5 is that. Now the structural formula goes like this. Now wait a minute. I've got 4 F's. I'm missing an F. 4 F's and 2 H's. Yeah, that's it. that is the structural formula for refrigerant R134A. It tells you that on table A.5. You know what they call that in chemistry? They call that a halogenated ethane. Remember what ethane is? Ethane is, that's ethane. What they've done is they've replaced 4 of the hydrogen with fluorine atoms. They call it halogenation. It's a halogenated ethane. I thought you'd be interested. I am not going to quiz you on that, but some of you might be chemical engineers, and that's what that is, and that's what my friend Reagan has in his car. Okay, now let's do a problem. We're going to do 241. Let me find it again. I got lost. It's in a sealed, rigid vessel, and it's saturated vapor. Okay. Now, Reagan, the secret to success in this class is this thing I'm drawing right here. And you know that.
Yes, I
You
do.
know that that PV diagram, that's where it's at. Okay, and we're dealing with R134A. Now go to the back and help me find R134A. Let me dig around in the back just a minute. I got to find it here. R134A. Yeah, found it. Now I always go to the vapor dome, or what they call the saturated chart table first, and see the top pressure up here at the very top is 4,064 kilopascals. But in our problem, 241, they don't tell us what the pressure is, do they? However, they say it's saturated vapor at 50, and 50 is right about here. And I'm going to draw the 50-degree isotherm. And you know how they go. They go like this. That's the 50-degree Celsius isotherm. Okay, let me keep reading here now. 241. It says saturated vapor. When it says saturated vapor, that's where you are, right there. They call it saturated vapor at 50 degrees Celsius. Well, we can get the pressure. What is the pressure at 50 degrees Celsius? It's 1318.1. Now, Reagan, can you find the 1318.1 on table B.5.1?
Okay.
Did you find it?
Not yet. Still looking.
Keep looking. I can wait. I want you to find at 50 degrees Celsius that pressure is 1318.1. And tell me when you do.
Okay. It's gonna be a little while. I have an electronic book. I got this,
Yes, so does everybody else. And if you know how to work it, you're a better man than I am.
I had a question, Professor.
Yeah, I'm listening.
So
Go ahead.
whenever you were finding that, is that a 4064 kilopascal, the top pressure?
Yes, that's supposed to be 4,064 kilopascals.
Just to clarify, you found that number by looking at a table. You're not actually looking at a chart like a picture of that chart, are you?
I should be on table B.5.1. Did I do something wrong? Let me see
No,
here.
not at all. I was just making sure that you weren't looking at an actual isotherm and copying it from the book, and you were just getting the information from the table.
No, I
So-
think this is correct. Now who am I
Okay.
talking to?
This is Taylor. I'm gonna go look it up in my
Taylor?
electronic book too and make sure I can find the same
Yeah,
value.
find it. Get your electronic book, table B.5.1, and you'll see that the very top of the dome is 4,064. But where we are is 1318.
That 4,064, that's at the very bottom of the
Yeah, it's
of
at the
table.
bottom of the table, but it's at the top of the vapor dome. See, it's just opposite. You understand?
So is that always the case that the pressure at the bottom of the table will be the top of the vapor dome?
That's right. Yeah. Good going.
Okay, thank you.
Now, yeah, anytime. Now
Perfect.
let's get the, yeah, go ahead.
I'm sorry to interrupt. That always
No,
corresponds.
fine.
This is Nathan. That always corresponds with the zero evaporation.
Yes, yes. It corresponds with the zero difference between the vapor and the liquid because they no longer have a VG and a VF anymore. See, this here has a VG and it has a VF, but when you get to the top, the difference is zero between those. And see, our specific volume will equal the VG here, which is, let me write it down now. We might need it. It's 0.01512. See if you can find it. You guys that are good with looking stuff up on electronics there. That's what it is. I need somebody to say, I found it.
I found it.
Yeah, good deal.
I did
Good.
not. Where are we finding that at? I'm sorry.
That should be on table B.5.1. And I think we're doing this problem for Reagan. Reagan, this is your problem, right?
Yes.
Yay, good. Okay. Well, now let me read it and see what they wanted us to do here. Saturated vapor is now cooled to 20. Okay, they're going to cool this off. But see, it's in a sealed, rigid vessel, so the specific volume is going to stay the same. We're going to follow this here till we get to a much colder temperature. We're going to cool it to 20 degrees Celsius. So let me do that. See, somewhere down here is the 20 degrees Celsius. And that is state 2 right there. No, not there. Right there. That's state 2. And see, we know the specific volume at state 2 is equal to the same thing we started with. So we got that. Here, let me do the device sketches. Let me draw the device sketches. Reagan, if you'll do this every time you do these problems, if you'll do the device sketches and the PV diagram, you'll be able to pass the course, okay?
Okay.
And here's the thing. You're right here at state 1. State 1. Now state 2. State 2. You know what? You were going to have to take off some weight. State 2 has got the same volume, but they took that weight off. See, the pressure is smaller, but the volume's the same. Now here's the difference. This one here has got nothing but vapor. Here, put some molecules of R134A in there. See, those little dots show up? Yeah, there you go. But state 2, look here, you got some liquid R134A here. And you got little dots here. You got R134A vapor, but you have a mixture at state 2 of vapor and liquid. The volume's the same, but the pressure is different. What about the temperature? Ooh, it got colder. Now, how did it get colder? Well, fill a bucket with cold water and stick this in it, and that'll cool it down, and you'll have a heat transfer out. If you stick that cylinder piston in a bucket of real cold water at 20 degrees, well, that's not real cold, but it's not warm either. It'll cool off, and so the temperature will be 20 degrees here, whereas the temperature here is 50 degrees. So there's our device sketches. The pressure here is 1318.1 kilopascals. Oh, I wonder what the pressure is here. Well, go to your table and look up 20 degrees Celsius and tell me what it says. Now we need R134A. I got lost. Okay, R134A. There it is. Look up 20 degrees. And the pressure there is 572.8 kilopascals. That's our new pressure. Pressure now is 572.8 kilopascals. Now, what are we supposed to do in this problem? Let's see. Let me read it here. It's now cooled to 20 degrees. Find the mass of the R134A and the quality in the final state. Okay. Well, the mass is going to be the same mass that you started with because it can't get out. If we can figure out what the mass is to start with, it's the same mass, right? Can't get out, so let's do that. And do we have room? Yeah, we got some room right here. Now here's the thing. We know what the specific volume is. And the specific volume is equal to the volume divided by the mass. Now we know what the specific volume is. We got it. This is the volume at 1. This is the volume at 2. They're the same. We got it. They give us the volume. They said the volume is 2 cubic meters. So we know that. That's given. It's 2 cubic meters. Hey, look here. Here's an equation. We know 2 out of 3 things. I know you can solve for the mass. Now, they wanted the quality, Reagan. Now, to get the quality, I need a little room here someplace. How about up here? Here's how you do it. I showed you this equation last time. We showed you where it came from. Now look, we know we're going to do the quality at state 2. Of course, it's the same as at state 1. So we know we know the specific volume, and hey, we can get this VF. I can tell you what it is. This VF at 20 degrees is, and let me shop around here. Here it is. It's 0.000817. And the quality of 2, we can find it. This VFG is at 20 degrees, 0.03524. 0.03524. So Reagan, we know this number. We know that number from the table. We know that number from the table. We can solve for the quality at state 2. I bet you can finish the, what do you think, Reagan? Can you finish that problem now?
Yes, I can. Yes.
Yay,
That's
good
fine.
going.
Thank
Good.
you for your help.
You are so very welcome. Anybody else before we move on to more exciting stuff? Okay, well, we need to know how to deal with English, senor. Habla inglés? Yeah, we're gonna do one with English now. So here we go. Let me erase all this. And we're gonna do one with English. I just need some room here. We're going to do a problem in English. This is problem 2-118E. Okay. Help me find it there. 2-118E.
Page P12.
Good going. Good going. I see it there. Now this is dealing with R410A. Now that's what I've got in my house. I won't go into the chemical and structural formulas because most of you guys aren't going to be chemical majors anyway. You're going to be mechanical, I bet. Aerospace or maybe a few civil. But we got our 410A now. Okay, got that. And let me write this down. It's 140 Fahrenheit. And, oh, they give you the specific volume. It's 0.5356. But see, we're in English. It's cubic feet per pound mass. Okay. All right. Oh, this looks like a nasty problem, but I can discuss it with you. We got time. We got time to work on it. Let's do the ideal gas model first. I tell you what would be fun is we can do it 3 ways. We're going to do it. We'll do it that way. And then we'll do it with the tables. We can just look it up. I think they have tables of R410A in the back. And then I think they want us to do it with compressibility. Well, we may not have time to do it all, but we'll try. Okay, tell you what, I want to do this one first because this is definitely the easiest way. Go to the back, help me find R410A. R410A, okay, I'm looking for it now. Hey, there it is. And we need 140 Fahrenheit. Uh-oh, I'm in the metric. I don't want the, let me try again, wrong table. R410A. Having a little trouble here. Trying to find it. There it is. Okay, I finally found it. And what we want is 140 Fahrenheit. Okay, and oh gee, they didn't give us the They didn't give us the pressure, did they? Well, here, let me draw the PV diagram to see where I'm at.
Professor, this is Nathan. Do we need to just convert Fahrenheit to Celsius real
No,
quick? No? Which-
never.
Which
Nathan,
take? Yes, sir.
we got to learn to work in the metric system.
English.
Don't convert anything. We got to learn to work in English. Don't convert anything.
Okay. What table are you on?
I tell you where I'm at right now. I'm at table F.9.1. F.9.1 is where I'm at. And I found 140 Fahrenheit. And here's what I found 140 Fahrenheit. Yeah, here we go. And I found this VF. See, 140 is actually up towards the top. It only goes up to 160. So it's about like here. (140 degrees Fahrenheit). There we go. (140 degrees Fahrenheit). Yeah. Okay. Now the VF at 140 Fahrenheit. This right here, that little VF thing, and here's a VG. Here, I'll write them down here. The VF is 0.01966. 0.01966. 0.01966. The VG is right in here. The VG is 0.0796. 0.0796. Well, you know what? 0.5 is bigger than either one of those. We are not in here. Do you understand? 0.5 is bigger than, we're out here someplace, guys. Here's state one. We're out here someplace. So,
Professor?
Yeah, go ahead.
I'm sorry. This is Nathan again.
Yeah.
Where are you getting the VF and VG from that table?
For 140 Fahrenheit, I'm looking at 140 Fahrenheit. I'm on table F.9.1, and VF is 0.01966. Can you find it?
No, sir. I don't have those numbers on table F91.
F.9.1.
140.
They don't have VF and VG on that table?
Does anybody else see that?
I have the physical book, but it does look like there's 2 pages to
There's
the
2 pages.
the
You're
saturated.
on the wrong page.
Yeah, it sounds like you're on the second page.
You're on the second page. You're doing
Thank you.
H's.
Thank you, Bryce. I'm good now.
You're good now. Good. Excellent. Okay. We're out in here, guys. But what are we supposed to find? I got lost here. Just a minute. Let me read this. Oh, we're supposed to find the pressure. Okay. Well, we can find it. But see, this is in the superheated vapor region. We're not going to find it on that vapor dome table. So go to the superheated vapor table. And what we need is 140 Fahrenheit with a specific volume of 0.5356. Okay, I'm shopping around now. And I'm shopping around. And Hey, we got real lucky, guys. If you go to where it says 150 PSI and the temperature is 140 Fahrenheit, the V is equal to 0.5356. We don't have to interpolate. And we're right there. And that pressure is 150. Come over here. This is 150 PSI. See this pressure right here at 140. I never wrote it down. I don't think I ever wrote it down. But at 140, there's two tables there, and we learned that, didn't we? At 140, the pressure is 556.488. PSI. We are right here, and we've got our pressure. We found, I think that's what they wanted. They wanted the pressure. They wanted the pressure. We found it for them. Okay. Is everybody okay so far?
I do
We
not.
just-
I do not see where you got the 150 psi. This is Nathan.
Oh, well, here, thanks. Let me show you where it is. Go to the superheated vapor table for R410A. It's table F.9.2. You need table F.9.2. Shop around till you can find the 150 PSI. Can you find it?
Yes.
Now look at the 140 Fahrenheit at 150 PSI. What does it say?
Let's see. I see where it says 150 and 140, 150 psi,
Yeah.
140 degrees. And what am I looking for?
You're looking for that little V, the specific volume.
0.5356.
Yeah, 0.5356. Well, that's what we're looking for. 0.5356. We have just found the pressure. It's 150. Got it? See, we got lucky. We didn't have to interpolate.
Got it. Yeah, thank you.
Yay, good going. Okay, now we used the table and we found the pressure, and it turned out to be 150 PSI. Okay, now what we're going to do is we're going to do the ideal gas law and get the pressure using it. Okay. You understood all that so far, I hope. If anybody just tuned in, we're doing problem 2, 118E, and now we're going to do the ideal gas model. I just need some room to work here. Well, you guys are taking notes. If I forget something, you can tell me what it is. You guys are paying attention and are awake pretty much. We're going to
Professor,
do the ideal. Go ahead.
I'm sorry to keep jumping in here, but this is Nathan.
No, I love it. Go ahead.
And I just want to make sure I understand. So you started with a saturated table so that you could find that your state one was outside of the vapor dome,
Yes.
and that's important because then that took us to the superheated vapor
Superheated
table,
vapor table.
and that's where we
Yes.
got our answer. Okay, all right.
Yes. Good going. But now, see, what we're going to do is we're going to go PV equals RT. Okay. Now we know the V. It's given. Here, let me write it. The V is given. It's 0.5356. it's in the problem. It's 0.5356. So we got that. But now we don't have R yet. We're going to have to look up R. Go to the back and help me shop around and find this value of R here. I'm shopping now. It's got to be in English, senor. And we want R 410E. Okay, R410E. Yeah, there it is. 410A, I mean. There it is. It's, I'm getting 21.29 foot-pound force per pound mass Rankine. Now that, I found that on table F.4. Table F.4. And I'll wait till I hear an uh-huh from the gang here. See if you can find that. Can you find it?
I found it fine.
Yeah, it's in the back. Good, good. Okay. Hey, look, we just found that. Now the temperature. Hey, I know the temperature. But it's got to be in absolute. It's got to be in Rankine. Now, what that is I think it's, oh, gee. Is it 359.67? I'm rusty. I'm going to have to look that up. I don't want to lie to you. That might be right from memory, but I don't trust me, okay? We're going to look that up. To get Rankine, temperature. You have to add, it's 459. You have to add 459.67 to get Rankine, okay? I found that in Appendix A1. Table A1 is where I found that number. So what you got to do is you got to add these up to get your Rankine, okay? So here's what you'll get. You got 599.67 Rankine. Here, let me write that down. This has got to be in absolute temperature. Now, if I make a mistake here and don't know how to add, somebody jump on me, but I think that's right. Okay, now we got that. Hey, look, we got the V, the R, and the T. We should be able to get the P. We got a nice equation, right? We can do that. But now there's a tiny problem with the units. To get the units to work, you've got to multiply this left side by 144 square inches is a square foot. Because see, these are going to be in cubic feet per pound mass. And you'll cancel the square feet. I could write that out for you if you wanted. Here, let's write it out so we can see this better. I need the room. I hate to erase this wonderful PV diagram, but I need the room. Now, what I'm going to do is I'm going to write this out. I got 144 inches squared per square foot. I have P, which we're trying to find. We know what it's in. It's in, no, it's in pounds force per square inch. That's what it's in. And then V, I have that. It's in cubic feet per pound mass. I have the R, it's 21, 29. and I have the Rankine temperature. It's 599.67 Rankine. Okay, now here's my equation. We know everything except the P, and we can solve for the P. Here goes. Now remember, we already know what the P is. It's 150 PSI. Isn't that what we got earlier? 150 PSI? Okay, plug all that in, tell me what you get. I didn't get 150, I got 143.2 PSI. Did anybody get 143 PSI? If you did, say uh-huh. Because I could be wrong. Plug all this in. We're solving for P now. You got all the numbers, just put it in your calculator and tell me what you got. That's what I got. What about my friend Nathan? What'd you get, Nathan?
I think I'm putting it in wrong, but I have 165.5.
Well, let me do it again. I could do this wrong. Let me try again.
To be honest, I'm not sure.
That's fine.
What
I'm
I'm
gonna do it
looking
again.
at.
You
What I'm
could be right and I could be wrong. Hey, good going. I'm getting 165.5. Anybody getting that? I think I was wrong the first time. Is
Yes.
that what you got?
That's what I got.
Yay. Anybody else?
I got 165.
Good. Excellent. Okay, now here's the deal. We did this with the tables. And we got, didn't we get 150 PSI? Isn't that what we got a little while ago? Somebody say, uh-huh.
Yes.
Yeah, that's what we got. And then we did it with the ideal gas law. And we got 165.5 PSI. Now we're going to do it with the compressibility. Oh, gee, we only have 8 minutes. I'm going to have to hurry. But I think I can do it. We got 8 minutes. You're going to do your homework. You're going to read your chapter.
Mr. Griffin,
Yeah, I'm listening.
where did you get this 144 inch square per feet?
Oh, there's 12 inches in a foot. And if you square it, you'll get 144 square inches. Whoops, this is wrong. Mohammed, that's supposed to be square feet. I'm gonna give Mohammed a thank you point there. That's supposed to be square feet. That's
Okay,
where I got it.
Okay, and also, how did you get the temperature 599.67? I'm confused on that. Why
How did I
you
get
add?
the 599? Okay, thank you for asking. What I did, Mohammed, was I took the temperature, which is 140, and I added to it 459.67. See, that's
Yeah.
Fahrenheit. When you do that, you'll get Rankine.
Where did you
And
get
it
this
should-
459.67?
Oh, thank you for asking. Mohammed, go to page, it's appendix A.1. Appendix A.1, and it's the third page of that. You go to appendix A.1, and to convert from Fahrenheit to Rankine, you have to add 459.67 to get Rankine. Do
Okay.
you remember with the metric you had to add 273.15, Mohammed? Do you remember
Yes.
that?
Yes. Yes.
But see, this is English. In English, you have to add 459.67.
Okay.
You okay now?
Yeah. Oh, okay.
Okay. Well, we've done it two different ways. Now this is the best way. The tables are always the best. I'm going to put a happy face right there. The tables are the best way. Now, this is off a little bit. I'm going to kind of put a little sour face on that one, okay? That one's not as good. Now, this should be in between. It should be a little bit happy, but maybe not quite as happy as the tables. Now, to do it, I need some room here someplace. I need room. I might not have time to finish this, but you could finish it. We need the reduced pressure and the reduced temperature. Remember we did those? Now what we need is R410A. So go to the back and help me locate. Oh, I'm running out of time. Go to the back and help me shop around. And I'm trying to find the R410A. Where the heck is R410A? I'm having trouble finding R410A. And there it is. I finally found it. There it is. And this is going to be well, see, here's the problem. We don't know the pressure, so you have to use what they call an iteration. We'll have to use the ideal gas as a starting point and divide by 711. You'll find that on table F.1. And for the reduced temperature, that was it 499? I erased it. Was it 499 something? Is that what it was? Help me. Help me, I'm running out of time. And the reduced temperature is 620. You have to divide by 620.1. I'm getting these numbers from table F.1. You guys aren't going to help me. Roughly, it's 460 plus 140, and that's 590.
Yeah, I think it was 599.67.
Well, yeah, it wasn't 499. It's 5. Thank you so very much. I appreciate your help. Yeah, that's much better. So you get when you add those, you get 600. That's close enough. Okay, we did great. Now let me get those. Oh, we're running out of time. Oh no, I only have 2 minutes left. But see, this is equal to a 150 divided by 711.21, and this one's equal to 599 divided by 620.1. That's equal to 0.97. And then you go to that graph that I told you about. And you find 0.97.
Okay.
Well, that's dang, 0.97 is dang close to 1, you know what? And then you go up, no, wrong one. We want 0.21, sorry. There's 0.1, there's 0.2, there's 0.21 right about there. And you go up to 0.97, which is dang close to 1. Let me show you where I think it is. It's just on this side of 1, and you want 0.21. I'm getting about 0.82. I wish I had a little more time with you, but I'm getting Z is 0.82. So when you go to figure the PV equals ZRT, you'll discover that the P you're trying to solve for the P is going to be a 0.82 times what we got. Now, what did we get? We got the 165. What's 0.82 times 165? Let me see what you get times 165.5. I'm getting 159.8. So using, is this showing? Yeah, this is showing up. Using a compressibility, I'm getting call it 160. We'll round it off to 160. I did that in a hurry because we're out of time. But this is the correct answer. We're getting 150 PSI. This is what we get with the ideal gas, 165. Now with compressibility, I got 160. It's a little better. It's a little better than the 165, but it's still off. But now you know about compressibility. And it's sad, but our time is up. Here's your last chance to say anything, because I'm gonna close our session.
Professor, is there any specific time when we turn in our homework? Is it as long as it's before the due date?
Yeah, any time before the due date.
Okay, thank you.
Yeah. Anything else from anybody?
Thank you.
Okay, well, thank you, guys. I'm going to say goodbye for now. I'll see you on Wednesday, okay? Wait, what's today? No, I'll see you on Thursday. Yeah, I will see you on Thursday. Goodbye, everyone.
Bye.
Bye.